We were speaking about the operation that we introduced today, which is the change of measure, because we are playing on a market which is characterized by a probability space, omega fp, in which p represents the so-called physical measure, the so-called market measure. The problem of this measure is that it is too much linked, and we will say more actually in the next class. It is too much linked to our subjectivity, so it might not represent the best measure under which we may want to work. We like to work on the measures that have some nice properties, like, for example, the fact that if we discount the price process or the value process of whatever asset, it is a martingale, like, for example, with a risk-neutral measure. I mean, we might also want to play with measures for which the modeling of specific events or specific parts of distributions is easier. So the typical situation is, for example, imagine that you are in a domain in which the phenomenon you are studying is characterized by highly risky tails, so extremely fat tails. We will say more, but heuristically speaking, that a fat tail is any tail that in the limit behaves like a power law, so it behaves like a Pareto distribution. And the point is that under that type of tails, it might be the case that some moments are not defined, some quantities we play with usually are not correctly defined, and we have to look for alternatives. Now, in the theoretical framework, a possibility is to change the measure such that we can try to govern the tail in a better way. If that is completely efficient also when we come back to reality, it's an open discussion, because we will see, I will try to show you with a few examples later when we play with Black-Scholes, that every time you move from the physical measure to the risk-neutral measure and back, you induce errors in your estimation. Sometimes these errors are known, so you know that there is an error, so you can take that into consideration and you can quantify the error. In other situations, it's not possible, so we have to be a little bit more heuristical in the solution. So what we are considering now is our usual probability space, omega fp, and what we want to do is to substitute this p with another measure. That for us will be the risk-neutral measure, because it has a lot of nice properties in pricing from the pricing point of view. But in general, it can be whatever measure. I just want to change this measure under one condition, that the new measure I introduce is equivalent to p. Equivalent, you remember, I told you, means that they agree on what is not possible and on what is possible. That is to say, if an event has probability 0 under p, it needs to have probability 0 under the new measure. If the probability is not 0, is positive probability, then they might give different numbers. This is not important. But they absolutely have to give probability 0 for events that are not possible. There is no other compromise. So what we want to do is to introduce this measure. Now, there are in the literature different ways in which we can move from one measure to the other. At the end of the day, they are all linked. So you can always move from one to the other. But the approach starts as a different approach in every situation. What we will consider in this course is mainly the use of the Radon-Nikodym derivative. But later, I will also show you another approach, which is more common in actuarial mathematics, so for insurance modeling, that is via distortions. So introducing a distortion as a way to create a new probability which is equivalent with respect to the one you started from. Now, the way in which we introduce this measure that is equivalent to p, and that later we will also show is risk neutral, but for the moment we don't know it, is by introducing the Radon-Nikodym derivative. Now, how can I move from p to another measure that we call already q, but that for the moment is not necessarily risk neutral. The idea is the following. We consider, so we start from the very basic probability 101 case, and then we rapidly move. We consider a random variable, z, which is positive, strictly positive, and such that the expectation of z under p is equal to 1. Now, you will see that now I will, most of the time, say the expectation with respect to one measure or the other, because now we're introducing different measures. So we want to be safe in understanding what type of expectation we are considering. So we consider a random variable z, which is positive, and such that the expectation of z under the measure p, which is our physical measure, is equal to 1. Then, for every f in our sigma algebra, what do we know? We know that the probability of f can be written as the expectation under p of the indicator of the event f. Okay, so this is trivially the expectation definition of probability. You define an event which is a Bernoulli event, and then you take the expectation corresponds to the probability of the event itself. So this is how we indicate the probability of the event f. Now, how can we introduce a measure q that is equivalent to p and that exploits this fact via z? So the idea is that from now on, we define q of f as the expectation under p of z, the indicator of f. What I can tell you is that defined in this way, q is a proper probability measure. Now, how can we prove that something is that a measure of the type is a proper probability measure? We have some conditions that need to be verified. So it needs to be something that is always non-negative, so it cannot be negative. It is something that essentially lies between 0 and 1. It means that if I consider the whole set, the mass, the measure assigns to the whole set is 1, and the mass, the measure assigns to the null set, so the complement, is 0. So it needs to be in these bounds. And it needs to be sigma additive. So we need countable additivity. Because if it is not sigma additive, it can still be, for example, a probability in the strict sense, but not a probability measure. So if you consider the big distinction between the Kolmogorov approach and the definite approach, in the definite approach, you don't need sigma additivity, because the idea is that it's a subjective approach. You will never have the time and the will and the measures to count up to infinity, so everything needs to be finite. It can be very large, but finite. So you don't need, in that approach, sigma additivity. So how can we prove that this guy is actually a probability measure? There is a proposition in the lecture notes, let's say. So you agree with me that Q of F is always non-negative. That's trivial. Y is the expectation of an indicator, which is 0, 1, and a positive random variable. Okay, it's the product of these two quantities. One is strictly positive, and the other one is 0, 1. Okay, so the fact that this is non-negative, it's trivial. Now, what happens if we consider the measure of the whole space? So if we consider the measure applied to the whole set omega, it should be 1 if this is a proper probability measure. Let's see if it is the case. So let's just substitute the definition. This is the expectation under P of Z, the indicator of the whole set. But trivially, the indicator of the whole set is 1. It's always verified. So what's the expectation of Z? By assumption, it is 1. So it works. What happens if I consider the null set on the contrary? I will have Q of the null set is the indicator of, well, sorry, is the expectation on the P of what? Of Z times the indicator of the null set. The indicator of the null set never verifies, is always 0, so you get 0. Now, the little more tricky thing is that we want to show that this is sigma additive. What does it mean? It means that if I consider a countable union of events in my sigma algebra, then the probability of the countable union is just the countable sum of the probabilities of the single events. So how can we do that? Imagine that we consider a sequence of events, F1, F2, F3, and so on, that all belong to our sigma algebra, and such that if I take the countable union of all these events, so the union for n from 1 to infinity of Fn, these are equal to an event F, which is contained in the sigma algebra. What I ask is that these events, F1, F2, and F3, are pairwise disjoint. Now, they are pairwise disjoint. And now what I want to do is to verify that if I take Q applied to the countable union, what I get is just the countable sum of the Q's applied to the single Fn. Now, how can I do that? I just start from my event F. So I take Q of F. Now, this is equal to what? This is equal to the expectation under P of Z, the indicator of F. Okay? Now, the point is, F is given as the countable union of all the other events, F1, F2, F3, F whatever. So, one simple thing that we can immediately notice is that this is equal to the expectation under Z of the infinite sum for n to 1 to infinity of the indicators of Fn. Now, this is equal, if you want, to the expectation under P of the infinite sum for n to equal to 1 infinity of Z, the indicator of Fn. And now, one thing is the following. Can I take my expectation of the sum? So can I take the expectation inside the sum and transform the expectation of the sum in the sum of the expectation? Yes, no, maybe? I can, but I have to be careful. Because this is not a finite sum. For a finite sum, don't even think about that. Do that. It enters. No problem. But this is a countable sum. Yet, we know this. So we can apply the monotone convergence theorem. And the monotone convergence theorem allows us to do that. So we can take the infinite sum, but it's important that we know that it's because of the monotone convergence theorem of the expectation under P of Z, the indicator of Fn, which is nothing more than the infinite sum of Q, F, N, which is what we want to do. So it's sigmatic. So it is a proper probability measure. That's very important to us because we want to play with this type of object. If you want, if you do not believe in sigma additivity, which is not the case for us in this course, but if you don't believe in sigma additivity, it can still be a proper probability in the definitive jar, Savage way, because of the fact that obviously it is also trivially finitely additive, and all the other requirements are satisfied. Now, given this way of introducing a new measure a new measure Q, starting from our measure P, and these two measures are equivalent. This is an exercise that you find in the lecture notes to prove. They are equivalent means that if I take an event F that has mass 0 for P, it needs to have mass 0 for Q. And if it has mass 0 for Q, it needs to have mass 0 for P. So this is what we had to show in order to prove equivalence. But in any case, we can do something more. We can build a relationship between the expectation under P and another expectation, which is the expectation under Q. Until now, we are playing with the expectation under P. So the question is, what happens if we want to build a connection between this and this? It is the following. Consider a random variable y, which is non-negative. If this is the case, we have that the expectation under Q of y is equal to the expectation under P of y z, where z is always our quantity there. And for what concerns the expectation under P of y, it can be expressed as the expectation under Q of y over z. Here, you should immediately see why we need z to be strictly positive, because we divide by z. Okay? Notice that if z is not strictly positive, but it is non-negative, obviously what I wrote here is not necessarily true, but you are still in the situation in which the probability of A being equal to 0 implies Q being equal to 0, the probability of Q being equal to 0. But not the opposite, because of this, because you lose this part. So if Z is non-negative, is not a proper way of finding an equivalent measure, but you can still build a new measure that inherits the sets of measure 0 from the first one. But it does not guarantee that you can also do the opposite, that you can also move in the opposite direction. Okay, this is the way in which we define our expectations. Okay? If we have a Z such that we can build these until here, we call this Z here Radon-Nikodym derivative. A common way of representing the Radon-Nikodym derivative Z is through the notation dq dp. And we say that Z is the Radon-Nikodym derivative of measure Q with respect to measure P. If you take 1 over Z, obviously you are defining the Radon-Nikodym derivative of measure P with respect to measure Q, which is actually what happens here. Now, this Radon-Nikodym derivative is very important because, first of all, in terms of definitions and notation, if I have a measure P and a measure Q such that there is a Radon-Nikodym derivative, and what I've written so far holds, we say that P and Q are mutually absolutely continuous. So mutually AC, absolutely continuous. And second, this notation here is also very nice because it gives us a very simple way of observing one fact, which is the following. So I think that it's one of the possible notations. It's not the only one, but it's quite useful to observe the following. What's the expectation on the Q of Y? Now, if I consider the expectation on the Q of Y, this is nothing more than the integral on the domain of definition, omega for us, of Y dq. Okay? But what can I do? I can always take my dq, introduce dp, dp. But this is equal to the integral over the domain of y z dp, which is equal to the expectation on the p of yz. Okay, so it's a nice way of putting everything together. Now, the big problem, once we know what a Radon-Nikodym derivative is essentially a strictly positive random variable with expectation 1 with respect to the measure from which we start. Now the problem is, yes, strictly positive random variable with expectation 1 is a little bit too generic. So we will have to find the proper random variable in the different situations. And you will see that, obviously, if I'm just interested in a point in time or one-shot phenomenon, it's just a random variable that is positive and expectation 1. But if I consider, for example, stochastic process, very likely the Radon-Nikodym derivative will be a collection of random variables, each one applying at a specific time or at a specific point in space, or depending on what is your indexing set. For us, most of the time is time. So what we have is that we will have a random variable for each time instant. So putting them together, we will have that our Radon-Nikodym is nothing more than a stochastic process. It's a collection of random variable indexed with respect to some set. Now, a very important result related to the Radon-Nikodym derivative, even if we have not yet specified, for example, what is the distribution of this Radon-Nikodym derivative or whatever, is the following fact. So we are considering our sigma algebra F. Now, what I tell you is that there is another sigma algebra G, which is contained in F. And I know that I have a Radon-Nikodym derivative dq dp that works on the sigma algebra F and allows us to move from P to Q and from Q to P if I take 1 over. Now, a question I can ask myself is, what happens if I want to restrict my attention to the sigma algebra G, which is included in our initial sigma algebra F? Now, luckily, we can observe the following. So let's Z be this guy. I can always compute dq dp restricted on G as the expectation under P of Z conditioned on G. Now, the proof of this is very simple. You find it in the lecture notes. So what we introduce now are two fundamental results of pricing theory that build on what we have seen so far. And given the great fantasy that we all share in mathematics, they are known as the fundamental theorems of asset pricing. There are two. The first theorem gives us an important information, and it tells us that if a market can be characterized by a risk-neutral measure, that is to say, I'm able to build a risk-neutral measure on that market, then under that measure, it is not possible to have an arbitrage. So if there is a risk-neutral measure, and I'm using that risk-neutral measure for my evaluations, it is not possible to have an arbitrage on the market. And this is extremely important, because you remember last time we gave the definition of arbitrage, of free lunch, and I told you that this is something that we don't want. So everyone is happy to earn money for free. We all agree on that. But it's a distortion for the market, and it does not allow the market to work properly. Also because, for many different reasons, some technical, some heuristical. Imagine that you know that there is a chance that someone makes money for sure, and you are not able to access that opportunity. The question you ask yourself is, if someone is making money for sure, since you cannot create wealth out of nothing, somebody is losing for sure, okay? And you don't want to be that somebody. So it's better to be on a fair field in which there is no arbitrage. And the first fundamental theorem of asset pricing guarantees that. The second fundamental theorem of asset pricing is even stronger, because it would be fundamental for us to play with this. As I told you, one of the reasons why we introduced the risk-neutral measure is to get rid of the ambiguities and the different perceptions that rely on the expectations, on the perceptions of the different agents on the market, on the different utility functions, if you think and if you believe in utility theory. So there are many possible justifications, but for sure, one way to justify the presence of the risk-neutral measure is that it needs to get rid of all the different possible evaluations. But then the problem is, what happens if I have two risk-neutral measures? Until now, I'm not saying that it's unique. I might have two different risk-neutral measures. Imagine that instead of Z, I have Z1, Z2, and that both are able to give me a risk-neutral measure. Then, which one should I choose? Because if I choose one risk-neutral measure and you choose the other, we are still in the same situation as before. Instead of your personal expectations, now we have two different risk-neutral measures. The second fundamental theorem of asset pricing takes care of that, giving conditions for the uniqueness of the risk-neutral measure. The problem of the second fundamental theorem of asset pricing is that those conditions are quite strong. So they might work in very, very, very good market conditions, but for sure they were not working yesterday. Okay? So that's the problem of the second fundamental theorem of asset pricing. Obviously, this is a theoretical course, so I just leave all the problems, all the real-world problems to my other course, which is QRN. In this course, everything works perfectly, so we don't care too much about the sad reality of things. Okay, so let's consider our first fundamental theorem of asset pricing. So probably after the break, but we can already introduce that. First fundamental theorem of asset pricing. Now you remember that last time I briefly gave you the definition of arbitrage. What is an arbitrage? An arbitrage is a portfolio whose value in T is Vt, but such that the value in 0 is equal to 0. Moreover, for our portfolio to be an arbitrage, we need two conditions to be satisfied. One is that the probability that Vt is non-negative, so that the value of the portfolio, let me be consistent in the notation, sorry. The probability that V capital T is non-negative is equal to 1. It means that at maturity, for sure, there is no loss for me, so it has a non-negative value. And the probability that V capital T is strictly positive is positive. This means that if I compute the expected value of my portfolio under P, this expected value is positive, because I have something that, in the worst case, is equal to 0 at maturity, but there is a positive probability of being positive, so the expected value needs to be positive. And that's why we call that an arbitrage. So for me, it has no cost, and essentially I can get money at the end, or at least I don't lose. So we don't want this. And the first fundamental theorem of asset pricing tells that this is not possible. It's not possible to have this portfolio. Now, since we will use that later, you agree with me that this condition here can be rewritten in this way. Okay? And this is from where we start after the break.